so let's remember what we're doing. Anybody want to tell me what we're doing?
We're dealing with some Cesaro and Abel's mobility.
That's right, that's right. So we're doing this thing called the Abel means. Abel means of the Fourier series. Right, so the story is, of course, that you don't get the function back pointwise, but if you do these sort of averaging tricks, then you actually can get the function back pointwise. So we create this thing, the Abel means, right? So this is summation, and when n equals negative infinity or positive infinity, r to the absolute value of n, a sub n, e to the I n theta, where f is an integrable function, and a sub n are the Fourier coefficients. A sub n are the Fourier coefficients. So we create this thing, and it turns out, so what we saw at the end of class last time was that, so we saw that in fact the Abel means can be realized as the convolution of f with the Poisson kernel, right? But with the rth Poisson kernel, right? Where Poisson kernel is this thing, summation r to n theta and from infinity to positive. Okay, and what Jaden asked at the end of class last time, can't you just look at the Fourier coefficients and say, well, look, they've got the same Fourier coefficients, and so they must be equal? That's actually true. That actually is true, right? Because you look at hey, hi. So right, so you say, well, look, if we look at the Fourier coefficients of this thing, well, it's just going to be the product. Oops. It's just going to be the product of the Fourier coefficients. The product of the Fourier coefficients, right? But the nth Fourier coefficient of the Poisson kernel is r to the absolute value of n. Right? So the Fourier coefficients are the same. So I'm just saying that Jaden is right. Right? And right, the Fourier coefficients of the Poisson of the Abel means are also r to the n, r to the absolute value of n times the Fourier coefficient of f. Right? This f was integrable, and p sub r is continuous because it was uniformly convergent. Like we saw, it's uniformly convergent. It's a uniformly convergent sum of continuous functions. So it's going to be continuous also. So this thing is the convolution is continuous, right? We saw that this guy was also continuous, and so you've got two continuous functions with the same Fourier coefficients. So it's the same thing. Okay. So yeah, so that's same fact. Okay. So so the point of this was that it's an example of the approximations of identity. So we want to say that that this thing actually is an approximation of the identity, and so we can use the theorems on it. Okay. So Lemma, Poisson kernel is an approximation of the identity. Okay, as r goes to 1. Okay, so we have to show the typical three things, right? That we need to show that the integral is 1, the the L1 norm is bounded, and that it has that concentration, satisfies the concentration requirement. Okay. So recall two things. One, that the Poisson, that this thing converges absolutely. And two, that that we had this expression for the Poisson kernel, right? The closed form expression, which was that this is going to be 1 minus the norm of omega squared over 1 minus omega quantity norm squared, where omega was R e to the omega. Right, and we also had we could write, that's the same thing as writing this 1 plus r squared minus 2 r cosine theta. Okay, so so the first thing is you say, well, this thing is positive, right? Because r is less than 1, right? So this thing on the top is positive, the thing on the bottom is positive. So we see that this thing is this thing is positive, right? And so we just need to show that the L1 norm is equal to 1, right? And then that'll be it. But that's pretty straightforward. You say, well, if you look at L1 norm, right, that's going to be the integral of this thing, summation r theta, d theta, but by the uniform convergence, we can change the order of integration, and so we get summation in the positive infinity, this Rn dθ theta, right? Which is going to be 0 except when n is equal to 0, right? And so we get 1. So I think we've seen this before. Right. So this is just change the order of integration. Right. So switch the summation and the integral, and then each of these guys is going to be 0 except when n is equal to 0. Right. So these are all. So only n equals 0. The only one that survives is n equals 0. Okay. Okay. So so now we need to prove the concentration thing, and for that we're going to use this 1 minus r squared over 1 plus r squared minus 2 to r cosine theta form. So so you say, okay, well, look, 1 plus r squared minus 2r cosine theta, we can rewrite as 1 minus r squared, 1 minus r quantity squared plus 2r, 1 minus cosine theta. And then we say, well, look, we're trying to show the concentration condition, right? So fix some delta, right? Fix some delta. So fix delta greater than 0, and we can assume that r is bigger than a half, because we're going to let r tend to 1, right? We're trying to show that as r tends to 1, that the thing bunches in inside here. Okay. So you say, well, okay. So assume that r is bigger than a half, and assume that the size of delta is bigger than I'm sorry, the size of theta is bigger than delta. Okay, and it's pretty straightforward, right? You just say, well, look, one minus something that's one minus something that's bigger than a half is going to be bigger than a half squared. Right, and then we have this 2r is bigger than 1, so this is going to be bigger than 1 minus cosine theta. But cosine theta, right, cosine is going to look something like this, right? So cosine theta is going to be smaller than cosine delta, right? So we get, if we subtract off cosine delta, it's going to get smaller, right? Cosine theta is, anyway, right? In any case, we get some constant that's dependent on delta that's bigger than 0. Okay. So what does that give us? That gives us that this thing, right, is smaller than 1 minus r squared over the constant that depends on delta. And so as r goes to 1, then this goes to 0, right? So so the limit as r goes to 1 of PR theta d theta for theta bigger than delta and smaller than pi, it's going to be 0. Okay. Okay. Anyway, so the point is that just like in the other case, we get that the Poisson kernel is an approximation of the identity, and so you get you get the convergence that you're hoping for, right? So you get if f is integrable on the circle. If f is integrable on the circle, then if theta naught is a point of continuity, then f convolved with p sub r theta actually converges to f of theta. Right. The Abel means converge at points of continuity. And right, if f is continuous, then of course the convergence of the Abel means to the function is uniform. Okay, so this is kind of like the good results with regard to pointwise convergence. Right? We were hoping for pointwise convergence of the Fourier series. We couldn't get it, but if we play these sort of averaging tricks, then because they turn out to be convolutions with good kernels, then we actually can recover the function pointwise. Okay, any questions? Easy enough. Okay, let's go on. So we're just going to show one application. We'll finish up this chapter by showing application to the Dirichlet problem. So okay, so recall we were in chapter 1, we talked about the Dirichlet problem, which was that you had some function and it was harmonic inside the unit disk, which we'll call D, and it was equal to some function on the boundary of D. And then at that time, we guessed that all solutions would be of the form. We guessed that all solutions would look like this, that Rn e to the I in theta, as m goes from negative infinity to positive infinity. That, in our current language, is the Abel means of the function, of the Fourier series of the function. Right. In other words, f convolved with p sub r theta. So now we'll have this theorem that says that this actually is, it's sort of like to what extent this is all solutions. So here's the theorem. So let f be an integrable function on the unit circle. So then, if we let u of r theta be f convolved with the Poisson kernel, the so-called Poisson integral of f, then that solves the heat equation on the disk. The steady state heat equation on the disk. In other words, U is twice continuously differentiable on the disk, and harmonic, and recovers the boundary value at points of continuity. So if f is continuous at theta, then the limit as r goes to 1 of u of r theta is f of theta. And of course, if f is continuous everywhere, then the convergence is uniform. And then there's a third part, that if f is continuous, then this is unique, right? Then this is the unique solution to the steady state heat equation on the disk. That such that it's harmonic, and we have this convergence. So, right, so this is the, in that case, this is the only solution. Okay, so, right, the Poisson integral is the unique solution to the steady state heat equation. Yeah, fine.
If, say, f is not continuous on the disk, is the idea that this still gives solutions because the discontinuity, like, already, wait, I'm not saying this very well. Yeah,
So it will,
let me understand the case where it's not continuous.
it will give a solution,
Yeah.
but that solution is not necessarily unique.
Okay, I see. But if it's not continuous on the boundary, then there's, like, in some sense, it already doesn't make sense as a mapping of heat, right? Because the heat wouldn't, like, the heat
Be
wouldn't
distinct.
jump in temperature.
That's
or-
true. Yeah,
Okay.
that's true. Yeah. So I guess in a real sense, this is the only solution.
Gotcha. Okay, cool. Thank you.
Okay, everybody all right? Okay, so okay, so let's prove these parts, right? First thing we want to do is show that the function is harmonic, right? So okay, so proof. So recall again that since f is integrable. We have this Fourier series expansion. Right. The Fourier, since f is integrable, the Fourier series expansion converges absolutely and uniformly. So if we on the disk where R is smaller than some rho, okay, so what we want is that this is going to converge uniformly and absolutely. So for theta, between 0 and 2 pi, and for r smaller than some rho. Okay. So it converges on that entire disk, okay. And as does as do the derivatives of the partial sums. Okay. What that allows you to do is to change the order of differentiation and summation. Okay, so this is this you might have seen you should have seen in your first analysis class, right? That if you have uniform convergence, of the series, if you have uniform convergence of the derivatives of the partial sums, and you have convergence of the original series at a single point, then that allows you to interchange differentiation and the infinite sum. So this is if you This is in root in chapter 7, if you want. Okay, so the point is that the series is infinitely differentiable, infinitely term by term differentiable. With respect to either r or theta. So with respect to r and theta. Okay, so so in order to show that this thing is harmonic, we want to use the harmonic. We want to use the polar form of the Laplacian. So recall the polar form of the Poisson. Right, that this is second partial with respect to r plus 1 over r first partial with respect to r plus 1 over r squared second partial with respect to theta. Okay, and so we just want to apply that to to this. Okay, so then differentiating term by term. Right, we just have to apply that to each of the terms, and it's pretty straightforward. It's just a calculation, right? So you get m absolute value of m, absolute value of m minus 1, r to the absolute value of m minus 2, e to the alpha theta, plus 1 over r, absolute value of m, r to the absolute value of m minus 1, e to the alpha theta, plus 1 over r squared, r to the absolute value of m, negative m squared e to the I theta. Right. So we get r to the m absolute value of m minus 2 in each of those cases, right? And so we get m times m minus 1. We get this. We get m squared minus m, and we have a negative m squared plus m, and so that cancels out. We get 0. So we get a bunch of zeros. Okay. So that's just calculus. Okay. So that gives us that the Poisson integral. When you take an integral function and then convolve it with the Poisson kernel, you get a harmonic function. Okay. Okay. Then the next thing you want to see is that thing actually it's harmonic on the disk, and you want to see what happens as you as you let r go to the as you tend towards the boundary, right? But in that case, we just go back to our previous theory, right? We know that the Poisson kernel is a good kernel, and so by what we just said, we're going to recover our function at continuous points, and the convergence is going to be uniform if the function is continuous. So part 2 we already did, right? So part 1 is to show that this is equal to 0 on the disk. Part 2 is to show that we recovered the boundary values, right? We want to show that where f is continuous, f convolved with this recovers f of x, right, as r goes to 1. Right? But that's exactly what we just we already proved. We just proved that. right? We want to show that, and that if f is continuous everywhere, then we get uniform convergence. Right? But that's exactly what we just did. Right? Okay. So the main trouble is to show the uniqueness. Okay. Okay. So so here we go. Suppose there's another solution. Suppose V r theta is another, twice continuously differentiable solution. Suppose f is continuous, right? And that we have another solution such that the Laplacian is 0, and that V r theta converges uniformly to f as r goes to 1. Okay, so first observe that. Second. Okay. So yeah. So recall that since each of these V's is twice differentiable, right? We know that the Fourier coefficients decay like 1 over n squared, and so the Fourier series actually does recover this function uniformly from the theorem in chapter 1, chapter 2. I'm not sure. Since this is twice differentiable, the Fourier series, its Fourier series converges uniformly to itself. Okay, so let's write this notation. V of r theta we'll write as summation a sub n r e to the I in theta. Okay, so the Fourier series is going to change with respect to r. So we'll write the Fourier series. The Fourier coefficients depend on r. So we have this d r theta e to the negative I in theta. Okay, so that's good. We have got this Fourier series that converges uniformly. This function is twice differentiable. Okay, and so now we want to show that that it's harmonic. Right. Okay, so. So, right, so we'll just apply, again, we'll apply the, we'll use the polar form of the Laplacian. We do have to invoke a theorem called the Leibniz differentiation theorem, which says that if you have a function on some interval, on some square, then and f is continuously differentiable. If f is continuously differentiable with respect to, sorry, just with respect to x, then you can change the order of integration. So if you look at this function and you're differentiating this function with respect to x, then you can change the order. You can slide the derivative inside. Okay. So we know that this equals 0. Thank you. Right. And now we take that and we integrate it. We integrate the whole thing over against. Sorry. We integrate the whole thing against e to the negative I and theta, and that'll still be 0. Okay, so now we invoke the Leibniz differentiation theorem. It says that in the integral of the derivative, we can actually pull the derivative through the integral. Right, so this is going to be ddr squared of 1 over 2 pi, negative pi to pi, v r theta, e to the negative I theta, theta, right, plus 1 over r ddr, same thing, v r theta, e to the negative I theta, theta, right, plus 1 over r squared, 1 over 2 pi, and we'll leave that, this one we'll leave on the inside. So second partial with respect to theta of v e to the negative I theta d theta. Okay. So we know that's equal to 0. Okay, but right, and this of course is the Fourier coefficient, right? This is the Fourier coefficient a sub n of r, right? So we get a second derivative of that guy plus 1 over r times the first derivative plus this last thing. And on this guy, we use integration by parts to shift the derivative over to the exponential 2 times. Okay, so we shift it over 2 times. We don't get any boundary term because this is periodic. The function is periodic. Both functions are periodic, right? And so all that happens is we shift that over 2 times, right? And so we get. Wait, so the derivative d on theta gets shifted over to here. So we have two derivatives with respect to theta here, and we get just negative n squared times a sub n r. So you get negative n squared times a sub n. Is that all right? Any questions?
So we're looking at the Fourier coefficients of the Laplacian of
We're,
and we're arguing that those have to be zero.
that's right, yeah,
Okay.
yeah. Okay, okay, so, okay, so we're almost done. This equation implies, and sorry, this is a homework problem. So chapter 1, number 11. It implies that that the a sub n's must be of a particular form. They must be some linear combination of r to the n and r to the negative n when n is not equal to 0. And in the case n equals 0, then it's a sub n plus b sub n log of r. Okay, so I'm just going to take that as a fact. Okay, and then you say, well, look, the a sub n of r's, right? That's the Fourier coefficient of v, right? E to negative I and theta d theta, right? Right, but those are all bounded, right? Those are all bounded because v is v was C2, right? So this is a twice continuous function on a disk, right? So this is bounded. So these guys are all bounded. Bounded by some constant. Okay. So what does that tell you? As n goes to infinity, r is less than 1, right? So this is greater, r to the negative 1 is greater than 1. As n goes to infinity, this is going to become arbitrarily large, right? So that tells you that sorry, no. As r goes to 0, as you let r go to 0, this becomes arbitrarily large, right? Right. And so the b sub n's must be all 0, right? So all the b sub n's must be 0. Let n go to 0. Let r go to 0. Right. So that tells you that a and r is capital A sub n r to the n, right? But then a sub n is going to be the limit as r goes to 1. The limit as r goes to 1 of a and r. Right, so it's the limit as r goes to 1 of 1 over 2 pi, this thing b r theta, e to the negative I and theta and theta. Right. Now remember that v converge uniformly to f as r goes to 1. So we can change the order of integration, right? And this just turns into the Fourier coefficient of f. you can do a similar argument for, so this is assuming that n is bigger than 0. And you could do a similar argument for n less than equal to 0 or n equal to 0. Yeah.
Sorry, I was trying to puzzle out how the differential equation works. Shouldn't we have an over r squared in that constant term? Otherwise, the r's have a different exponents. I think.
Oh yeah.
It's a small thing. I just.
No, you're right. You're right. There should be an r squared.
Thank you. Yeah.
Okay. So, right. So what do we get? That right. Remember, VR theta was this e to the in theta. I think so. Sorry, no, sorry. R to the n, e to the in theta. Right. And so, and these guys all turn out to be the Fourier coefficients of n. And so that's the same thing as what u was. Right. So yeah, so we see that the solution is unique. Okay, so next time we're going to go, so this was sort of like the end of the, the pointwise convergence results. And the next time we're going to go into the sort of the more natural setting for Fourier series, which is L2.